Most of the things we do here, we're never going to get to see again. It's emotional to take something you spent years of your life on and put it on a rocket and probably never see it again. It ups the pressure on getting that sequence of events right. We've got 1 hour of descent time and one shot to do this. So we have to make sure that we're resilient to things like if our computer hangs up and has to get reset partway down, if we lose communications with the satellite. We've got all sorts of things that we need to make sure that we cover as contingencies, because there's no going back and trying again.
This is NASA's Curious Universe. Our universe is a wild and wonderful place. I'm your host, Patty Boyd, and in this podcast, NASA is your tour guide. Our home planet, Earth, is so hospitable for us, for living things, and for the structures and tools we create. But outside of Earth, that's not necessarily the case. When we plan missions to send science off the Earth, we have to prepare for inhospitable circumstances, whether it's a deep space probe like the far-out Voyager spacecrafts, an experiment on the International Space Station, or a vehicle headed to another planet. We need to send the right tools to do the job. But how do we know what to make our spacecraft out of? And how do we decide where to start? Today, we're going to talk to a scientist and an engineer on one of NASA's newest projects, the Da Vinci mission, to broaden our understanding of our planetary neighbor, Venus. How exactly do we design and build spacecraft to make these harrowing trips through dangerous and exciting environments?
You know what is so great about mission work? If you love thinking about multiple things at a time, this is a job for you.
That's Stephanie Getty, the Deputy Principal Investigator for the Da Vinci mission. Da Vinci will leave the Earth in 2029, headed for a hostile and mysterious mission. This will be groundbreaking science, but we here at Curious Universe have toured Venus and Da Vinci before in an episode from Season 3.
So the Venus we see now is a puzzle piece. In the 2020s, we have the glimmers of what might have been. An oceanic world that lost its oceans. Perhaps after billions of years of oceanic, beautiful, habitable world environments, something went awry. Something changed it to be the world of today. Those things and those questions are important because they tell us what can go wrong.
In case you've forgotten some of the specifics, let's have a bit of a refresher.
So Da Vinci stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. It is a mission that is going to fly by the planet Venus on its way to getting into position to drop a spherical probe through the atmosphere and measure what the atmosphere is made of at regular points as the probe descends.
The Da Vinci team has a big task ahead of them. Create something that will fly through space and land on the surface of another planet, all while sending information back here to Earth. Luckily, they're just going next door. Venus is our planetary neighbor, and there are a lot of ways in which Venus is similar to Earth, but just as many things that make it very, very different.
Venus is about the same size as Earth. It's not that different in its orbit around the sun. It's got clouds around it. It's got rocks on the surface. It's got solid landforms, a lot like Earth, but it's got vast differences too. It's got major differences from Earth as well, in that it's clearly had major volcanic activity on its surface, more so than Earth in recent history. Its clouds are not made of water vapor like on Earth. They're made of sulfuric acid. And the surface temperatures are not Earth-like at all. It's about twice the temperature your oven at home gets to, so it's about 900 degrees Fahrenheit at the surface of Venus. And the pressure is 90 times the pressure at the surface of the Earth. You can imagine going about a half mile into the ocean, and that type of pressure is what you would feel in the carbon dioxide atmosphere at Venus.
When you get ready in the morning, you probably think about what you might wear if it rains, what cup will keep your coffee warm, and maybe if you'll need headlights to drive. There are all kinds of environments, scenarios, and tasks NASA spacecraft have to take into account too. Scientists keep all of these in mind when designing the spacecraft, in addition to the science goals of the mission itself.
Not only do we have to design to survive what's known as the cruise stage, the part of the mission where the spacecraft is going through deep space, it's going from Earth to its destination, but we also have to think about what happens when we get there. So we'll launch on a rocket that will vibrate our spacecraft, and we need to make sure that our spacecraft survives that vibration. We need to make sure that our spacecraft survives the vacuum of space, the cold temperatures, the radiation from the sun. We will fly by Venus twice. That means orbiting the sun a couple of times. And then on our third pass by Venus, we'll deploy our sphere, entering the atmosphere, having to withstand the friction of the high speeds with the atmosphere, thinking about the variations in pressure that it'll experience from a very low pressure environment of space to the high pressure environment of the surface. That's a wide range of conditions that the entire mission needs to consider.
As you might imagine, it takes a big team working together to make all the different parts suitable for all the different scenarios the spacecraft may encounter. The scientists study and plan the things they'd like a spacecraft to do, and then it's up to the engineers to come in and make it happen.
Usually you want to get started with the science question. What's driving us? What do we need to learn? And then coming up with a system that can meet that. Hi, everyone. I'm Matt Garrison. I'm a systems engineer at NASA Goddard. We help the scientists come up with what their mission needs to be, what we can design and build and operate to meet their science needs. And then we get to see it the whole way through. We get to come up with the design, we get to analyze it, we get to put it together and test it, take it to the launch site, and sometimes actually get to operate it once it's up in flight. You get this really wide experience of things, and it means that stuff's always changing. You'll spend a bunch of time designing something. By the time you're tired of the design process, good, you need to go build it now.
So where do we begin? One of the first things we need to consider when building a spacecraft is what it should be made of.
The materials are really driven by what the thing has to do. DAVINCI has a bunch of really interesting material challenges because of the Venus environment. The atmosphere of Venus is a really nasty place.
Let's get into some specifics. As Stephanie mentioned, Venus is not exactly a tourist destination. It has a hot, poisonous, high-pressure atmosphere with dense, noxious clouds. As if that weren't hard enough, DAVINCI will be entering that atmosphere unpiloted from space, a maneuver which is tricky enough here on Earth.
When we hit the atmosphere, we're going to decelerate at about 40 Gs. I went and did some math on that, and my laptop at 40 Gs weighs about 100 pounds.
40 Gs means 40 times the power of Earth's gravity. That's a lot of force on your spacecraft. A human could survive 8 Gs, but only for a few seconds, and it would be really uncomfortable. Imagine that times 5.
Once we descend a little bit further, we get into the clouds, and the clouds are about 80% concentration of sulfuric acid. Sulfuric acid is used to etch steel, but usually at the 10 to 20% range. So we're talking many times higher concentration acid than you use to do like industrial etching. The atmosphere is also really thick. As you descend further in, the temperature and the pressure are increasing. By the time you get to the Venus surface, it's about 900 Fahrenheit, which is the temperature of a good wood-fired pizza oven. And the pressure is about 90 atmospheres, which is the equivalent of about 1 kilometer deep in the ocean, which is about the average depth of the Arctic Ocean. So if you've got something that can operate inside your pizza oven at the bottom of the Arctic Ocean, that's the kind of environment you're looking for.
Easy, right? We're making something to take in as much groundbreaking science as possible on a planet over 38 million miles from Earth that has to withstand the conditions of an underwater pizza oven. Luckily, we're building on a legacy of space travel. The US and Russia have each visited Venus before.
August 26th, the Mariner 2 countdown begins. Events move on a strict timetable.
5, 4, 3, 2, 1.
But no new spacecraft have descended through Venus's atmosphere since 1985. Past voyages to Venus and other solar system bodies have taught us a lot about how to travel through space. Plus, we've got some pretty smart friends helping us out.
We have other systems that we can kind of rely on as a starting point. Da Vinci's carrier spacecraft is coming from Lockheed Martin, and they've got a history of building spacecraft like this. We can kind of rely on some of their previous design to get a leg up on ours. We've got instruments on Da Vinci coming from NASA Goddard, from Johns Hopkins, from Malin Space Science Systems, and from the Jet Propulsion Lab. Then you're really building a team based on who has expertise in delivering the components you need to address those science goals.
For all the new things we need to invent? Well, that takes brainstorming, problem solving, chemistry, math, and more. Before it was even submitted as a proposal, the Da Vinci team had to design and test some of the components to prove it could work.
Early on, when we're coming up with designs, usually you try to find the things that are new and risky, and you try to make something like that early on and run some tests on it. They call it verification and validation. Verification is, did we build the thing right? And validation is, did we build the right thing? And that's where we get into a whole lot of our really interesting test setups, where we're putting things in big thermal vac chambers, pumping them down to a vacuum, and running them through temperature cycles. Put it on a shaker table. We're putting them in a special electromagnetic facility where we can blast them with radio waves and make sure that we don't have noise on our signals. And for Da Vinci, we're actually building a custom facility to simulate that harsh Venus environment. We're getting a special facility that can go do over 90 atmospheres of pressure and really high temperatures in order to prove out that our mechanical and thermal design will actually work. So that when it all comes together, you've got a satellite or a mission that accomplishes your goals.
So, what are the materials that will take us to Venus? It turns out they aren't as wild or wacky as you might imagine.
It's actually pretty standard stuff. The descent sphere is made out of mostly titanium. The spacecraft is kind of standard materials that Lockheed's used to working with. We have some composite, some aluminum. And even the window that we're looking through that has to be exposed to that environment, it's sapphire glass, lab-grown sapphire. It's really resilient, but it gets used pretty regularly.
Getting all of this done can take a long time. So where exactly are we in the life cycle of the Da Vinci mission?
The timeline of a mission is typically 5 or 6 years long. That gives you enough time to design the mission, to build some test articles, to evaluate how those test articles behave, and then refine your design so that you're ready to build the real thing that's going to go to Venus. We are on the early stages right now of that process. Our planned launch readiness date is in June of 2029. So right now we're in the stage where we're evaluating our design. We're looking at things that might go wrong, that might pose challenges to us as we design and build the mission. And we're studying the best way to tackle those challenges right now before we get into the phase where we start to really nail things down and define how exactly we're going to build the hardware.
We often get to speak with people who are at the end of a mission, seeing their project that they've poured years into finally leave the Earth and begin its scientific journey. This team is at the very beginning of this exciting mission. And part of planning from the beginning means figuring out how it will end. Da Vinci will take in incredible information as it passes by and descends into Venus's atmosphere. But even with all this careful planning, testing, and safeguarding, it still won't fully survive the harsh conditions of Venus. DAVINCI's descent probe will only last about an hour before it gets destroyed in Venus's high-pressure, toxic atmosphere.
So the descent sphere will, at some point, stop working. Even if it survives the landing and even if the instruments are still operating, there will come a time when the temperature and the pressure will become too much, and we'll have to say goodbye and thanks for the service. The spacecraft part that carried the descent sphere to Venus will still be flying off in space. It is possible that that will have a life beyond the central mission, but right now what we are designing the mission for is to do the 2 science flybys, the probe drop-off, and then the spacecraft will also be done with its service. What I'm cautioning myself not to do is think too much about what the sphere is experiencing, because it's going to be unpleasant. We're still early. We don't have the hardware yet that we can go up and hug, which we would not do because you need to keep it clean. I do think about us as a team on Earth, sitting in a control room together, hopefully, or a science operations center, experiencing the culmination of all of this hard work. There's a small number of really exciting moments in a mission like this. One is when you get off the launch pad and you say goodbye to your mission with your own eyes and wish it good luck. There will be a first flyby 6 months after launch. We'll all gather and we'll encourage everybody on Earth to gather with us to see these new images of Venus, the Venus clouds on the day side, and then the glowing infrared images on the night side. But the descent through the atmosphere, it's hard to describe. It's that gratification to see all of the hard work that the team has put in, really culminating in this incredible moment. 59 minutes. In the time that it takes to watch an episode of The Great British Baking Show, our little descent sphere that's the size of, a largish beach ball will make revolutionary new measurements about our nearest neighbor, Venus, and allow the science community to answer these incredibly important and long-standing questions about Venus as our neighboring planet. That's very momentous. And then a little bittersweet, right? Because then we'll be thinking about the little descent sphere on the surface of Venus getting baked and crushed by the pressures. But, it will have done an incredible job for us and for humanity.
This remarkable machine, carefully designed, built, and tested by countless thoughtful scientists and engineers, will show us so much more about our neighbor planet than we've ever known before. At this stage, figuring out what we can do and how we can do it serves as the building blocks for future missions. The more we learn about how to safely explore hazardous environments now, the further out we can reach in the next generation of exploration. When we figure out the technology to open those doors and withstand harsh conditions, who knows what else we can find? This is NASA's Curious Universe. This episode was written and produced by Christina Dana. Our executive producer is Katie Conans. The Curious Universe team includes Maddie Arnold and Michaela Sosby, with support from Christian Elliott. Our theme song was composed by Matt Russo and Andrew Santaguida of System Sounds. Special thanks to Giada Arney, Jim Garvin, and Nancy Neal Jones. To learn more about all the exciting spacecraft heading out to explore our solar system, check out solarsystem.nasa.gov/missions. Still curious about NASA? You can send us questions about this episode or a previous one, and we'll try to track down the answers. You can email a voice recording or send a written note to nasa-curiousuniverse@mail.nasa.gov. Go to nasa.gov/curiousuniverse for more information. And remember, you can follow NASA's Curious Universe in your favorite podcast app to get a notification each time we post a new episode.
Great work. Okay, next line is top of page 10.
Da Vinci's descent probe will only last about an hour before it gets destroyed in Venus's high-pressure, toxic atmosphere. It's sort of like if you tossed a frisbee onto your neighbor's roof, but the roof is poisonous, and there's no one there to toss it back.
I'm not sure about that analogy. I was trying something there. I don't know if it's going to stick.
It's not a perfect analogy, but one that people probably understand pretty well.